All right. So this is my project on space-based computing. It's my presentation. So first off, I know you guys are asking, what is space-based computing? Space-based computing is essentially when we use satellites, orbital servers, spaceborne platforms to store, process, and transmit our data. It's kind of like cloud computing, but the whole basis is that it's in space and not physically. It doesn't have physically have servers on the ground. So instead of relying on, the earthbound data centers, the idea is to move things either in below Earth orbit, what we'll be referring to that as an LEO, or on satellites and space stations. Why is this important in 2025? So the digital landscape is expanding beyond Earth. We may not always have the areas to make these large server rooms that store petabytes and zettabytes of data. And our cyber threats being off the ground is one way we can keep them safe from a military aspect. So here are some of the advancements in computer science and why these are important. Um, we're using AI and machine learning in orbit. We're doing edge computing at a global scale, cybersecurity and quantum communications, distributed computing and intersatellite network, and integration with ground-based platforms. Here's my first article on the classification of space-based computing systems by Marian Alsach. So here's a little rundown of the article. This paper presents a structured classification of the space-based computing systems based on architecture, functionality, and mission requirements. It compares centralized, distributed, and hybrid computing models in orbit and outlines how different satellite networks can be used to process, store, and transmit data. The study also discusses technical challenges such as latency, fault tolerance, data limitations, and power limitations, and highlights the importance of system adaptability for different space missions, which can be scientific, commercial, they call them, recreational use as well. Key points. Discussing limitations in space systems including latency, power use, and bandwidth. It also emphasizes onboard data processing to reduce the need for constant communication with Earth, which is part of that data limitation that I was talking about. It stresses fault tolerance and autonomy as key long-term to as key to long-term satellite operations. And it also encourages adaptable design to meet mission-specific requirements. So the importance of this article and why it's relevant to my project is because it provides a foundational classification of space-based computing systems. It helps explain how different architectures such as centralized, distributed, and hybrid support mission types and support technological needs and my research. It also supports my research by outlining key design challenges such as fault tolerance, power limitations, and data handling, which are important when applying space-based computing to cybersecurity, AI, and global data systems, as well as military cyber warfare. An overview of onboard processing architectures for space applications. This is my second article by Sarthak Verma. Um, it's a quick article overview. It basically reviews the evolution and current state of onboard processing architectures used in spacecraft and satellites. It analyzes how onboard systems are designed to handle increasing data loads and the demands of autonomy in modern missions. Um, it it evaluates computing hardware platforms like FPGAs, GPUs, and SoCs, and radiation hardened processors, and explains the trade-offs in power efficiency, reliability, and computational performance. The most important things to take away from this article are the fact that it reviews those emerging onboard structures, highlights the design trade-offs, emphasis on real-time data processing for autonomy and mission flexibility, um, and that it discusses the move towards modular and scalable hardware systems. It notes that the growing role of AI and machine learning workloads and onboard satellites is very important. As machine learning is constantly evolving, our space travel is constantly evolving. We saw the whole Katy Perry and the women in space movement that was important, or things like Claude coming out and saying that they tried to make a new version and deleted itself. It also addresses space environment constraints, including thermal limits and reliability, which is basically like, you don't want your processors to overheat on their way to space. Then they'll be fried in space. So that's just money, millions of dollars wasted. This article is relevant because it explains how onboard computing systems are evolving, which is what I was talking about, those processors. Um, directly relates to key projects like AI, machine learning in orbit, and autonomous space-based computing. Um, it highlights the hardware trade-offs and design decisions needed for secure and efficient orbital computing, and it supports the project's focus on building resilient, modular architectures for global data and cybersecurity operations in space. My third article by Rong Wu is Space slash Aerial Assisted Computation Computing Offloading for IoT Applications, learning-based approach. So the development of 5G and Internet of Things has enabled applications like VR and autonomous driving, which require high computing power and low latency. While cloud computing helps reduce device workload, it introduces delays due to long transmission distances. Mobile edge computing solves this by placing computer resources closer to users, improving speed and energy efficiency. This article also highlights ongoing research and task offloading, latency reduction, and optimizable computer communication and computing at the edge. So the reason why the key points to take away from this are that cloud computing helps offload heavy processing, but it also does introduce high latency. So the reason this is important is the goal is to have these centers is to have clouds so fast that we can put these centers in space and they can now like almost like a GPS satellite react just as fast. So our advancements in cloud computing are eventually going to help us be able to do things like autonomous driving, whether you have UAVs flying, or other things such as self-driving cars one day or the name right now. Your sensors, Wi-Fi 7, all of these things can eventually be done via satellite in space. My last article is space-based cloud fog and computer architecture and its applications by Tariq Taleb. Quick summary, the article highlights the growing demand for space-based information networks and the challenges caused by limited onboard processing of satellites. As satellite image data has increased dramatically, current downlink speeds can't keep up, creating bandwidth bottlenecks. Real-time applications like disaster alerts and remote sensing now require data rates beyond 1 GB per second, far exceeding the capacity of existing systems. Space-based data volumes have increased up to 400 times due to advanced imaging payloads. Current satellite ground transmission bandwidth is insufficient. This is basically saying why we need to donate more money into building these space infrastructures because we see that they can be used to benefit society, but until they get the funding that they need to increase bandwidth speeds, increase onboard computing, and increase the data structures that are already being sent back, then they may not be able to, they won't be as fast as we could possibly use them. U.S. military third-gen satellites are only 375 megabits of total bandwidth. That's less than the 1 GB we need for, current demand. So it's just to highlight the urgent need of in-orbit processing and the better satellite networks. This is important to my article because it reinforces my argument that in-orbit edge computing is the solution to latency and data overload. So again, that edge computing, that onboard computing, it's all the key. So supporting that and funding that is everything that we need it to be. So in conclusion, we know the digital landscape is expanding beyond Earth. Like I said about the data centers, the world is changing. It's 2025. Space-based systems enhance global communication, surveillance, and cyber defense, as well as, we use Google Maps every day. We use Apple Maps every day. These are all just important factors that we need, that not need, but that we use in everyday life. Our cell phones, your security systems back at home, all of this is space-based via satellite. And then from a military aspect, cyber threats are growing more sophisticated. And if you're the first one to secure that orbital infrastructure, then you can guarantee your country's security. Yeah, this is my presentation on space-based computing for Dr. Mia Moore's Intro to Comp Sci class.